Hi, my name is Mohammad Amin Ajdari, a senior researcher at Sharif University of Technology and HPDS Corp. In this talk, I would present an enterprise-grade open-source data reduction architecture for all flash storage systems. This is a joint work with my fellow researchers and Professor Hossein Asadi and Professor Andre Brinkman. In recent years, modern IO-intensive applications such as big databases and machine learning have demanded high performance and capacity. This has resulted in switching from the slow HDDs to fast SSDs with 50x higher performance, thus switching SAN storage systems from HDD arrays to all-flash SSD arrays. But SSDs have two major problems. First, an order of magnitude more expensive than HDDs. Second, tolerating limited number of writes on SSD cells before SSDs break. To mitigate these problems, data reduction techniques consisting of deduplication and compression are frequently used. Deduplication first eliminates data blocks with exactly same content. To reduce data footprint further, compression eliminates redundancies in each remaining block, and compressed non-duplicate blocks are finally written to the SSD array. The overall data reduction in real-world primary data scenarios may reduce storage requirements by up to 90%. But designing a high-performance data reduction architecture for industry-grade storage stack is very difficult. Let's look at how complexity of an industry-grade data reduction affects the performance with two examples. We use Red Hat Video, a promising open-source industry-grade data reduction module. First, we observe that the default data reduction module degrades performance by 3x due to complex reliability and metadata management operations. However, with a random access workload that has 90% data reduction potential, one can expect 10x less SSD bandwidth usage, thus 10x higher overall throughput. Second, data reduction has complex interactions with other modules, such as RAID controller write cache. We observe that the baseline all-flash work best with a write-through cache, but in all-flash system with integrated data reduction, write-through cache degrades performance by half. These results motivate the need for a detailed system analysis and re-architecting the storage stack to work best with data reduction. Following the motivational data, we first evaluate a storage system under various design choices from hardware layer to software layer. On top of the SSD array, we use an enterprise-grade hardware RAID controller, and we modify 4 parameters in this layer. In software layer, we analyze the effect of data reduction consistency mode. After finding the best design points, we also propose 2 software stack optimizations to maximize overall performance. As system setup, we use 9 Samsung SM863A SSDs, MegaRAID 9361 RAID controller, and as applications, we use synthetic workloads and real workload models Rhinebound VDBench, the popular IO benchmarking tool. In the following slides, we present a couple of our novel findings, and for simplicity and brevity, only show the results of random small write or sequential large write workloads with 90% data reduction potential. However, more detailed analysis and figures going beyond today's scope can be found in the full paper. As the first design choice, we analyze the effect of RAID type on system performance. We look at the 6 SSD setup using 3 major RAID types, namely RAID 5 with 1 disk as parity, RAID 6 with 2 disks as parity, and RAID 10 with 3 disks as mirrored data disks. We observe that in the baseline all-flash system, parity-based RAIDs have 3x lower performance than RAID 10 due to frequent read-modify writes and parity updates in random access to small write workloads. However, when data reduction is added to the storage stack, it partly converts random accesses to sequential data writes. Data reduction complexity also reduces the performance. This eliminates the performance gap of different rates in the presence of data reduction. Thus, our first finding suggests that rate type highly affects the performance in traditional all-flash systems, but the opposite is true in the presence of enterprise-grade data reduction. Therefore, optimal rate type can be selected following the reliability requirements, not the performance, in the all-flash systems with integrated data reduction, thus achieving a higher economy of cost. As a second design choice, we analyze the effect of RAID span depth on performance. As a reminder, span depth is the number of separate RAID arrays which are aggregated as a larger array. For example, with 6 data disks, we can make an array of RAID 5 with 1 span and 7 total disks. Using the same 6 data disks, we can make a 2-span RAID 5 with each group containing 3 data disks, and even 3 spans with each group containing 2 data disks. In this slide, we can see the performance result of the baseline all-flash versus all-flash plus data reduction under a random access small write workload. We observe that increasing the number of spans almost linearly increases the performance in the baseline due to more parallel opportunities of parity updates and lookups. However, the data reduction converts random accesses to sequential block allocation, and with additional metadata overheads, resulting in overall negligible performance change with span increase. This interesting finding leads to a new best practice that for the baseline all-flash systems, maximizing the number of spans helps the performance, but with data reduction present, it is best to minimize the number of spans to reduce the number of SSDs and their cost accordingly. The third design choice is RAID stripe unit size. This is the unit size of distributing data across different SSDs of an array. We compare the default value that is 256 kilobyte with the minimum value that is 64 kilobyte that our commercial hardware RAID controller supports. In random small write workloads, a stripe unit has almost no effect on performance. However, with integrated data reduction, 64 kilobyte stripe units provide 1.8x higher IOPS than 256 kilobyte stripe units. For sequential large write workloads, again, selected stripe units has no effect on performance of the baseline, as 4 megabyte blocks are already multiple of 256 kilobyte stripe units. However, with data reduction and average submitted IO requests from VDO in the range of 20 kilobyte to 30 kilobytes, smaller stripe units provide less read-modify writes and higher performance. In short, selected stripe units have no effect for the baseline running write-intensive workloads, but smaller stripe units improve the performance when data reduction is present. This suggests choosing smaller stripe units for all-flash systems with integrated data reduction, while this choice is less critical for the baseline all-flash systems. The fourth important system design choice is about the RAID controller write cache. Some commercial hardware RAID controllers have a small write cache on board. We want to evaluate the impact of this cache on the performance of an all-flash system versus an all-flash system with integrated data reduction. We observe that similar to existing best practice of disabling the write cache for all flash systems, write cache causes cache contention and can degrade the all-flash performance by 41% in random small write workloads. However, we revealed that the data reduction completely changes this behavior. Due to small granularity and partial sequentiality of IO accesses from the data reduction layer to the RAID controller, the write-back cache provides IO coalescing opportunities and boosts the performance by 37%. This suggests a new best practice. Enabling a write-back cache on the data path of an all-flash system with integrated data reduction is necessary, while the opposite should be followed for the baseline all-flash systems. The fifth important parameter is about how a data reduction module should guarantee data write consistency. Two modes exist with Red Hat Video, namely video sync mode and async mode. The sync mode guarantees a strong consistency for all applications by first writing all data to SSDs and acknowledging to clients, then starting data reduction operations. As async mode has additional write overheads, as sync mode has additional write overheads, the async mode exists as well. The async mode acknowledges the requests to the clients much sooner before the data are written to the SSDs, unless the application requires a stronger consistency for a specific set of I/O requests. We observe that in workloads with sequential large block writes, the majority of write overheads are due to the initial data writes to SSDs, and thus video async mode eliminates them and boosts the system performance by 2x. For random small block writes, video async mode also reduces the write overheads, but the overheads and speed up is smaller than sequential workloads. Thus, as a best practice, we recommend to only provide strong consistency on demand, that is, video async mode, to unlock high performance potential. So far, we have showed 5 new findings on tuning the performance of an all-flash with integrated data reduction. Are there any opportunities for further improvement? The answer is yes. We observe that our presented 5 tunings still leaves a 40x higher overhead of the tuned video versus the optimal data reduction implementation. 50% of the remaining overheads are read-only operations for duplicate detection through fingerprint lookups and data duplicate verification. The other 37% is for metadata updates. This means that most of the I/O overheads are for metadata accesses, and metadata are usually 1%, less than 1% of the whole storage space. Thus, we propose 2 additional optimizations using I/O caching and metadata offloading. In the following slides, we briefly go over such optimizations. Our first software stack optimization focuses on block fingerprint lookups in duplicate detection. These fingerprints require physical space, which is a few gigabytes for 100 terabyte storage capacity. Thus, we propose a fast read-only I/O caching below video to service fingerprint lookups from fast DRAM instead of SSDs. With a small-sized cache that can hold the fingerprints and the hot content, 78% of read overheads are eliminated, and we achieve 2x performance boost. Interestingly, the remaining overheads belong to other metadata accesses and exhibit different behavior, demanding the second optimization. Our second optimization is to accelerate address maps and journal updates of data reduction. Such metadata require very small space, for example, about 256 megabytes for journals, and less than 1% of storage space for address maps. Thus, we modify video to first disaggregate data and metadata block regions and place the block maps at the last 1% of the address space. We then offload such metadata accesses to a fast, non-volatile persistent memory. Offloading the block maps and journals to a fast, fairly small memory removes all remaining overheads and provides 3x additional speedup. This result emphasizes that data and metadata disaggregation and using proper memory device for each data and metadata type is necessary for high performance all flash plus data reduction system. This is how our final proposed architecture looks like. Note that our performance evaluations are based on our real prototype in industry-grade SAN storage stack. Overall, Our proposed optimizations and tunings provide a speedup of 12.5x in random write workloads compared to a partially tuned all-fly system with integrated data reduction. In addition, compared to the baseline all-fly systems without data reduction, our optimizations boost the performance per cost by 57x. In conclusion, we proposed an almost optimal architecture for an all-fly system with integrated data reduction and revealed new best practices for enterprise-grade systems. Our proposed architecture boosts the cost effectiveness by 57x compared to the baseline all-fly systems. As a final note, I encourage you to read our paper for more interesting details. Thank you for your attention. I'm now ready to answer your questions.